In this video, we're going to take a more in-depth look at the mechanisms for SN1 versus SN2 reactions. Now, we saw in the last video that SN1 reactions have 3 steps, and SN2 reactions have 2 steps. So what this means is for each step is going to have a couple characteristics in an energy diagram. So they're going to have a reactant, going to a product, and then in between this, we have what's called a transition state. This is sometimes abbreviated as a double dagger. So transition states are unstable intermediates between reactants and products. They are usually very hard to characterize. They are transient. They come and go very quickly, and they're usually high energy. So these are usually hard to isolate, if possible at all. They're usually predicted computationally, but they're in between reactants and products. Now, if these products are not the terminal products, we call this an intermediate. So an intermediate is not the end goal. It's something that is produced in one step and used up in the next step. So intermediates are transient as well. Intermediates usually can be isolated and characterized, but again, if they're high energy, it is something that would be examined computationally. Now, in examining energy diagrams, let's talk about the different parts of an energy diagram. So this is usually called the reaction coordinate. This is as the reaction proceeds from left to right, and we'll have energy on the y-axis. And this can be energy. Sometimes this is delta H, sometimes this is delta G. Actually, they wouldn't be delta, they would just be H and G. But in this case, we'll usually just call it energy to indicate just a general energy. So in an energy diagram, we're going to have 2 states. We're going to have our reactants, and we're going to have our products. And what we're going to see is we're going to curve up, and we're going to come back down. And in between here, this point right here, this is our transition state. So that's our double dagger. And that's indicated by this energy here, which we call our activation energy. And the activation energy can be large or small, depending on how kinetically favorable or unfavorable a reaction is. And then, so EA, or activation energy, this is governed by kinetics. And then our energy here, this is our delta H, or our delta G, or a delta E. This is our thermodynamic governed space. So this is thermodynamically governed. So kinetics, our activation energy, will tell us the speed of a reaction, and the difference in energy between the reactants and the products will tell us the thermodynamically favorable, whether something is thermodynamically favorable or not. Remember, in a case like this, where the products are higher in energy than the reactants, we would call this endothermic. And if the opposite was true, we would call it exothermic. Now, examining a more complicated energy diagram, let's say we have something that looks like this. So we curve up, and then we have one product here, and then we curve up again, and then we end up at our ultimate product here. So we would start with our reactants. So this would be our reactants. And then this point here, this is what we call an intermediate. We see it's not the terminal product, which we see over here. It is something that is going to be generated and then used up. We have an energy, an activation energy here. We'll call this EA1. And then we have an activation energy here, which we would call EA2. This would be our first transition state, and this would be our second transition state. Now, the comparison between activation energies will usually tell us what's called the rate determining step. So usually the larger activation energy will indicate which one is the rate determining step, and we'll talk about that a little more in depth further on in the video. So when we're examining energy diagrams, it is important to understand what's called, It's important to understand what's called Hammond's postulate. So Hammond's postulate says that if two states are similar in energy, that they are similar in structure. So if two states are similar in energy, then they are similar in structure. So what this tells us practically is if a transition state is closer to the reactants, it will resemble the reactants. Similarly, if a transition state is closer to the products, it will resemble the products. So looking at these in terms of energy diagrams, we can have a state that is closer to the reactants, and we can have a state that's closer to the products. So in this first case, our transition state is closer in energy to the reactants. We would call this an early transition state. And we see this, as we can see, the reactants are higher in energy than the products. So this is exothermic. So in general, exothermic reactions have an early transition state. In this case on the right, we see that the transition state is closer to the products. We would call this a late transition state. And we would see that this is endothermic. So in general, endothermic reactions are going to be have late transition states where the transition state is closer in energy to the product. So now that we have this information, let's examine the energy diagrams for SN1 and SN2 reactions. So let's start with the arguably more complicated one, which is the SN1 reaction. So as we saw, SN1 reactions have 3 steps. That means there's going to be 3 transition states. We're going to have 3 distinct transitions that we go through to get to an SN1 reaction. So let's examine this step by step and then put it together. So step 1, that's going to be protonation. So we have, looking at the example we had before, we have T-butanol plus HCl, and we'll draw the arrows. So we have the alcohol attacking the H and pushing onto the Cl. We are left with the alkyl oxonium ion plus Cl minus. Now, if we were to draw an energy diagram for this procedure, or for this step in the mechanism. Now, I said in the last video, this is a fast reaction, and acid-base reactions are almost always exothermic. As an exothermic reaction, we can predict this will be an early transition state. So we'll see, so this is E, this is our reaction coordinate. So we see an early transition state that comes down. This is going to be, and I'll draw these small in here, so this is OH plus HCl. Our intermediate in this case, since it's not the end of the reaction, this is our OH2 plus Cl minus. And what we see in a transition state is we see that this OH bond is starting to form and this HCl bond is starting to break. So just drawing that, we see that we have OH and we have HCl. And what I'll do is I'll draw dotted lines to indicate that this bond is forming and this bond is breaking. So we have a transition state where we're transferring a proton. We're doing proton transfer from this HCl to this alcohol. So this would be our transition state. And in general, transition states are drawn in brackets with that double dagger to indicate that they are not part of the reaction. They are simply transition states. Here's our activation energy, and what we would see is this activation energy is relatively small because this is going to be a kinetically fast reaction. So acid-base reactions are kinetically fast, so we see a small activation energy in this case. So our first step in the reaction is going to be acid-base chemistry. It is protonation of the alcohol to form the alkyl oxonium ion. So let's look at step 2. So step 2 is going to be the carbocation formation. So as we saw, we have the alkyl oxonium ion. The alkyl oxonium ion will have dissociation of water. We're going to break that CO bond, and what we'll end up with is a carbocation. plus water. Now, this is our slow step. And slow steps in the reaction are often what we call the rate determining step. Rate determining step meaning this reaction here is going to govern how fast the overall reaction is going to be, the overall transformation from the alcohol to the alkyl halide. So this slow step, this rate determining step, really determines how fast the overall reaction is. And what this means is, as we saw, kinetics are governed by activation energy. So what this is going to indicate is this has a high activation energy. What we can also see is the rate of this reaction is going to be governed by the rate law, which is governed by the concentration of the alkyl oxonium ion. Remember, rate laws are governed by the reactants of the particular reaction. This K here is going to tell us about EA. So the larger K, the smaller the EA. And if we look at the energy diagram for this, we can see that the EA is totally dependent on the structure of this alcohol. So the structure of ROH determines the overall rate here. And this is particularly for an SN1 mechanism. So what we see is if we have and I'll draw some carbocations. So I have a methyl carbocation, I have a primary carbocation, I then have a secondary carbocation, and then I'm going to draw a tertiary carbocation with 3 R groups around it. And what we see is that a methyl carbocation reacts much, much slower than a primary, which reacts slower than a secondary, which reacts slower than a tertiary. And I'll just label these down here: methyl, primary, secondary, tertiary. And I forgot to indicate these are carbocations. So what we see is that a tertiary carbocation coming from remember, this is coming from a tertiary alcohol, is going to be much faster, is going to have a much smaller K, or much larger K rather, than a secondary alcohol, which is going to be much, much faster than a primary, which is going to be much, much faster than a methyl alcohol. And this is the trend in stability. So this is the trend in stability that we see for carbocations that are formed as an intermediate. So let's talk about why this occurs. So the trend in stability, I'll rewrite this. So we saw that methyl is slower than primary, is slower than secondary, is slower than tertiary. So there's a couple reasons. This is the trend in stability of C+. So this goes methyl in the direction of tertiary. So why is a tertiary carbocation more stable than a secondary, primary, or methyl? So the main reason is that alkyl groups disperse a positive charge. And there's 2 main ways this does this. The first way is induction or inductive effects. So in an induction, this means that a sigma bond can polarize, meaning that we have, so if we're looking at a sigma bond that looks something like this, so again, sigma bonds look like this. Evenly distributed. If it's a nonpolar bond, it's evenly distributed. But say we have a positive charge on one of the carbons, we can actually see a sigma bond redistribution such that we're going to put more electron density on the side of the positive charge to kind of, what we could essentially say, negate the positive charge or even out the positive charge. So we see this inductive effects where sigma bonds will shift to balance out a positive charge that is occurring on a carbon. So what this means is if you have more sigma bonds with carbons around it, then you're going to have better stabilization of a positive charge. The second effect is called hyperconjugation. So hyperconjugation says that bonds beta to a carbocation can delocalize their electrons. If we're looking at various carbons or a carbon chain, say we have a positive charge here, and I'll draw in just a couple more bonds. We would say the bonds directly connected to the carbocation are the alpha bonds. So these would be alpha. We would say these are beta. And then one more out would be gamma. And you could imagine this going as far as you want. So what we see, just comparing two different carbocations, if you have a methyl carbocation, if we label these bonds, we only have alpha bonds, so there's no hyperconjugation that can occur in a methyl carbocation. Plus, the sigma bond between a carbon and a hydrogen is much smaller than the sigma bond between a carbon and a carbon. So we're doubly affected because we don't really have much inductive effects going on, and we have no hyperconjugation that's occurring. However, and this is going to be a little bit messy, say we have a tertiary carbocation. This is a tertiary carbocation. This is a terbutyl carbocation. If we look, here are alpha bonds. And look at all these beta bonds that we have. We have 3 on each carbon. We have quite a bit of beta bonding that's occurring near this carbocation, which means that we have quite a great deal of hyperconjugation occurring in a tertiary carbocation that does not occur in a methyl carbocation. So we see the stability is twofold. It comes from inductive effects, so the more carbons we have around a carbocation, the greater we have that sigma bond polarization to stabilize the positive charge. Plus, the more carbons we have around a central carbocation, we're going to have more hyperconjugation occurring to stabilize that positive charge. We're going to delocalize these electrons quite a bit more than we would in a methyl carbocation. So what this means is if we can stabilize the carbocation, we're going to reduce the activation. So if we stabilize the carbocation, remember it's unlikely for it to form because it's forming an unstable intermediate. However, if we can stabilize the carbocation, we're going to speed up the reaction. So what that means is that for a methyl or a primary carbocation forming, it's so unlikely that this is not the reaction mechanism we see. And that's why we had to introduce SN2 mechanisms. We don't see methyl and primary reacting via SN1 because they do not want to form this carbocation. It's not stable in this intermediate. However, secondary and tertiary will form the carbocation intermediate and are stabilized by inductive effects and hyperconjugation, such that secondary and tertiary alcohols can react via this mechanism. The methyl and primary activation energies are much too high to react via. So this is a very high activation energy in this step, whereas secondary and tertiary activation energies are lower. They're still quite a bit high. They're still high, but they're much lower than methyl and primary, and allow it to react via this mechanism. So let's look at what the transition states and what the energy diagram would look like for this. So again, we have our chart, we have our reaction coordinate, and we have energy. We would have our alkyl oxonium ion down here. That's our plus charge. We have our carbocation formed up here, and we have H2O on the side. I draw this uphill because this is thermodynamically unfavorable. We're forming an unstable species as an intermediate, so this is going to be unfavorable. And we draw the activation energy very high. So we would see that this is our transition state, and our transition state would look something like this bond breaking. So we'd have a partial, what we'd see is we'd have a partial positive charge on that carbon. We'd have water with still a partial positive charge and this bond starting to break. So this would be our transition state here. Now this activation energy is dictated again by the stability of the carbocation intermediate. So we would see that for a tertiary carbocation, maybe this is tertiary, so we see some amount of activation energy. If we had a secondary carbocation, we would raise it quite a bit more, so this would be secondary. And then if we had a primary carbocation, this would be off the chart. So I'm going to have it even going off the page. So this would be primary or methyl. So this activation energy is too high, so we wouldn't see this reacting via an SN1 mechanism. We would have to do it via an SN2 mechanism. But we see that this activation energy is reasonable for a tertiary or a secondary carbocation. Just as a further note, this is endothermic. We see the reactants go uphill to the products, and we see this is a late transition state because it is closer in energy to the products than the reactants. The final stage in this mechanism is quick, and it's going to be favorable. Remember, step 3 is going to be recombination with the X minus ion that was generated. That's this mechanism here. So we have the positive charge, we have Cl minus. We simply have electrostatic interaction dictate the mechanism for this step, and we are resulting with the overall product, which is the alkyl chloride. Again, this stage in the mechanism is going to be favorable and downhill. So we'd see something like this. We'd see an early transition state. So this is early, and it's going to be exothermic, where our reactants would be the carbocation and Cl minus. Our product would be the alkyl chloride, and the intermediate would be some kind of delta positive here, some kind of delta negative here, and we start forming the bond, the transition state. We start forming the bond between those two, and that would be our transition state. Again, early transition state, exothermic, very favorable. So let's examine what the overall energy diagram for this would look like. So let's draw a big one here. Again, this is the reaction coordinate. This is our energy. And let's start. So our first step is going to be favorable and downhill. I'm going to start midway. It's going to have a low activation energy, and it's going to go downhill. So again, this is our ROH plus HX going to ROH2 plus X minus. So that's the protonation of the alcohol. This is going to be a very small activation energy. It's fast, and it's going to be exothermic. The next step in the mechanism, this is our rate determining step. So this is going to have a high activation energy, and it's going to be endothermic because it's unfavorable. So we're going to have a peak. We're going to have a transition state. Again, this is transition state 1. This is transition state 2. We're going to have, this is our carbocation formation plus water. And then, again, unfavorable, this is going to be our high activation energy, and that's dictated by the structure of the alcohol. This is EA2, and this is our rate determining step. That's EA1. And then finally, we're going to have a very downhill reaction. This is recombination of the two positive and negative charges. So this is going, and you have a Cl minus, or X minus rather, floating around here. And you're going to have the recombination of those two products to form, I guess I switched halfway through from R to terbutyl. I'll just draw this as a terbutyl. And this would form the alkyl halide. And this would be very downhill. Overall, this reaction is generally exothermic if it's favorable, and this is encouraged by heating the reaction quite a bit. So this would be the overall. Again, we have step 1, we have step 2, and we have step 3. So overall, it's exothermic. The rate determining step is step 2, and it's determined by the structure of the alcohol. whether it's secondary or tertiary. Now let's examine, in comparison, let's examine an SN2 mechanism. So SN2 mechanisms are shorter. SN2, remember, it's only 2 steps. It's protonation and then nucleophilic attack. So let's look at this in one diagram. So remember, we're going to have protonation of the alcohol. That's going to be the same exothermic downhill, favorable. So let's see, we'll look at this reaction here. We'll look at this primary alcohol plus HBr goes to the alkyl bromide plus H2O. So in this case, we have our ROH, our ethanol, plus HBr. Our first step is going to be the protonation of the alcohol, just the same as it proceeds in an SN1 mechanism. So this is our OH2, our alkyl oxonium ion plus Br minus. And then we have one step instead of 2. This is going to be a high activation energy and a overall exothermic reaction. But this is going to be our high activation energy. This is our, so indicate here, this is EA1, and this is our transition state. This is EA2, and this is our transition state. This is going to be our rate determining step here, this nucleophilic attack, and this is also designated by the structure. If you can imagine, if we have a, let's just look at this alcohol, and I'll draw the hydrogens in here. And I'll draw a similar alcohol. So this is our methyl alcohol, and this is our primary alcohol. We're having the same backside attack. We have bromide and bromide. This can occur. We do have a backside attack on the primary alcohol to form the alkyl bromide, but we see that it's much faster with the methyl alcohol than the primary alcohol because these H's are much smaller than having a methyl group or an alkyl group, whatever that length of that chain would be. So we see that methyl alcohols for SN2 are going to react much faster than primary alcohols. So we'll see that methyl alcohols will have a smaller activation energy than primary alcohol. So we could say that this is a primary alcohol. They do both proceed quickly, but we do see the kinetics are affected a little bit by the changing from a methyl to a primary alcohol. And finally, just to round this out, we see that the ultimate step is substitution by the bromide on the H2O group. So again, 2 steps, 2 transition states, overall exothermic. It is remember this one's bimolecular because the rate determining step has 2 reactants in it. And it is, again, 2 steps. And we see that methyl alcohols will react faster than primary alcohols in an SN2 reaction.